everybody. Today's practice problem comes from Principles of Microeconomics, 6th edition by Gregory Mankiw. We're going to be doing Chapter 8, problem number 11. This problem is mathematically a little bit more advanced than other ones that we've been doing, but it does illustrate some important concepts, so I thought it would be helpful to go through. So it says, suppose that a market is described by the following supply and demand equations. And then it says that the quantity supplied in our market was just equal to 2p, and the quantity demanded in our market was just equal to 300 minus p. And if we were to graph these, we would see that this gives, a regular looking upward sloping supply curve and downward sloping demand curve. But let's think about if we can do this algebraically rather than having to graph everything and then, graphing it to scale to find the intersections and so on and so forth. We can actually do this solely with the equations that we're given. So the first part of the problem just says solve for the equilibrium price and the equilibrium quantity. So in a free market, we see that these prices that we both labeled as P, it actually makes sense to label them both as P because whatever price is relevant for the producer is also relevant for the consumer because there's no tax splitting those up, right, or making those different. So we can say that the condition for equilibrium is just that the quantity supplied in a market has to equal the quantity demanded in that market. So given this equilibrium condition, we can just plug in these equations here and solve for price. So we would see 2p equals 300 minus p. So this would just be by pulling this over, we would get 3p equals 300. Or P star, which is what we use to refer to an equilibrium price, is 100. And then to find the equilibrium quantity, we plug in this P star to either one of our equations. By definition, it doesn't matter which one. So we could say now that our Q star, again star for equilibrium, is equal to either 2 times 100, which is 200, or 300 minus 100, which is also 200. So we get an equilibrium price and quantity that look like something here. Part B of the question now says, suppose that a tax of an amount T is placed on buyers. And then it specifically gives us the new demand equation. So it's actually trying to make this easier for us than it would be otherwise. And it says now that the quantity demanded once the tax is put in place is not just 300 minus P, it's equal to 300 minus P plus T. And this is actually simply representing the fact that now once this tax is put in place, consumers not only have to think about the price that goes to the producer, which is what we call P, and used to be the same as what they were paying, but they also have to pay the tax. So we see here that this P was just replaced by P plus T. So this is the new demand curve. The supply curve is actually still the same. So we still have Q sub S equals 2P. And then it says solve for the new equilibrium. So we can do that. And then it's asking us to think about what happens to the price received by sellers, the price paid by buyers, and the quantities sold, which are those typical things that we usually think about when doing our supply and demand graphs. So let's do this. We still know that equilibrium is defined by quantity supplied equals quantity demanded. So again, we can just plug in and we can solve for P. We just have to think a little bit more carefully this time about what that means. So we can say here 2P equals 300 minus now P plus T. So we can distribute this negative, just do a little bit of arithmetic. 2P equals 300 minus P minus T. Don't forget to distribute that properly. And again, we can pull this P over, and we can say 3P is equal to 300 minus T. And we can divide both sides to see that now P is equal to, well, 300 minus 3 is 100, and T, or 300 divided by 3, sorry, my bad, is 100, and T divided by 3 is just T over 3. Now, this is a little bit strange because we specifically labeled this as P, but it's worth going back and thinking about what this actually represents. And you'll notice that the P was the price that was directly used for the supply curve. So what we've represented by P is actually the price that the producer gets to keep net of the tax. So it probably is more clear if we call this P sub P like we'd been doing before graphically. We can then go back and think about, well, what's our price to the consumer? And hey, guess what? Our price to the consumer, because the consumer is paying the producer, but also paying the tax. So we're going to have this relationship here. We can just plug in for P sub P and say this is just 100 minus T over 3 plus T. So this is just going to be 100 plus 2T over 3. And this is interesting to note, just bring this PC down here, because in accordance with what we've been expecting and what we've been seeing graphically, once we put this tax on the market, the price to the producer is lower than what it was before. Remember, our free market price was 100. And now the producer is getting 100 minus T over 3. So he's out a third of whatever that tax was. And the consumer is paying more than $100, right? Paying more than the original equilibrium price. Because the consumer's price is 100 plus 2T over 3. So essentially what we're seeing is that the consumer is bearing 2/3 of this tax burden, or 2/3 of the tax incidence, because its price increased by 2T over 3. And the producer is bearing 1/3 of the total tax burden, or 1/3 of the tax incidence, because its price went down by 1/3 of the tax. So we essentially see the consumer is paying twice as much of the tax than the producer is. And as a last step, we could go through and figure out what our quantity transacted with the tax is. To do that, we want to come back to here and think about either our quantity supplied or our quantity demanded. It's probably easier to think about this guy, because all we have to do is multiply by 2. So we just have to remember that our quantity, our Q star sub T, if we're finding it from the original supply curve, make sure we plug in the right price. And we said that the supply curve was in terms of the price that the producer gets to keep. So we have to make sure that as our equilibrium quantity, we're doing 2 times this price to the producer. So 2 times 100 minus T over 3, which is just going to be 200 minus 2T over 3. And again, we can see a number of things. We can see, one, that this is a lower quantity than was transacted in the free market, as we were expecting. So we've shown now through this example that taxes do in fact discourage economic activity in most cases. We could also see, if we wanted to, we could go through this exercise using the demand equation and confirm that we actually get the same thing, which we would, because we would just get 300 minus all of this plus T, which would again give us this. And if you're ever bored, you can work that arithmetic out for yourself. I actually broke my own rule a little bit over here, because I said we could do this all algebraically without thinking about our diagrams at all, but I did think that it would be helpful for you to see how everything translates from one point on the diagram to the other. So here you'll notice I just took the original free market price and quantity and labeled them here. So our market has an original quantity of 200, an original price of 100, and then took the numbers when the tax is put in place. So again, we have a price to the consumer, we have a price to the producer, and we have an equilibrium quantity with the tax, and those just go price to the consumer is the intersection with the demand curve at the new quantity. Price to the producer is just the intersection with the supply curve at the new quantity, and then the new quantity is obviously the new quantity once the tax is put in place. So if it's helpful to think about, you have this picture here to show how it all corresponds to what we've done here. So we can come back to the question now. And the question asks us a few other things. It says, tax revenue is T times Q. More specifically, tax revenue is T times Q star sub T, right? Because tax revenue can only be collected on units that are still being bought and sold after the tax is put in place. So we can think about this. We can say government revenue is equal to the per unit amount of the tax times how many units are still being bought and sold once the tax is put in place. So it tells us that. And then it says, use your answer to the previous parts to solve for tax revenue as a function of T. So we can go through and we can say, well, this is just going to be T. We don't need to plug in for that because that's what this is supposed to be in terms of, times this here. So T times 200 minus 2T over 3. So we get something like this. And we could multiply this out, and we could see that this is 200T minus 2/3 T squared. So this would be our formula for government revenue. And then the question says, graph this relationship for T between 0 and 300. So I'll go through in a second and I'll actually give you a graph that does this to scale. But even without that, we can see that the way that this is, just mathematically, is going to be an upside down parabola. Because if we're going to graph this as a function of T, we're going to get something that has T on the x-axis and then government revenue on the y-axis. And we're going to see, because the coefficient on T squared is negative, that we're going to get a parabola that opens downward. And we also notice that because there's no numerical constant in this, that the graph is going to start at the origin. Because obviously if the tax was 0, the government revenue would be 0. So we're going to get something that in general looks like this here. That we're going to get back to some positive tax amount here. And we could figure out what that is. I think it's at 300. Because if we were to solve this, we would see if we plugged in 300 that we would again get 0. So we're going to get something that looks like this. And we would even get something in this particular case symmetric, so that this was at 150. And that's going to be correct given that we started with straight line supply and demand curves. Unclear how realistic that is as an overall assumption. But nonetheless, we're going to get something like this. And what we've actually done is we've derived what's known as a Laffer curve, which just shows the relationship between tax rate and the revenue collected from that tax. So let's pause for a second. I'm just going to put in a 2-scale diagram for you here so you can look at it for a couple seconds. Okay, hopefully you like that. But nonetheless, what we're seeing from this is that for a while, as we're increasing our tax rate, we're actually increasing the revenue that we're collecting from that tax. But there's going to be a certain point where increasing the tax rate further actually decreases rather than increases the revenue that was collected from that tax. The next part of the problem says, the deadweight loss of a tax is the area of the triangle between the supply and demand curves. So that's not as well defined as I would like it to be, but we do know from what we've seen graphically before is that the deadweight loss from a tax is the area of this triangle here. And that's simply because the deadweight loss is found here simply because this is the region where units used to be transacted before the tax was put in place, but the tax caused these units to not be transacted. So it took away whatever value was being created from transacting those units, and the vertical distance between the valuation to the consumer and the cost to the producer is in fact the amount of value that was taken away for each unit. So that's why we get this deadweight loss, being this triangle here. Nonetheless, we can think about the area of this triangle, or equivalently our deadweight loss, as just 1/2 times base times height. And if we think about this triangle sort of on its side, we can think of the tax rate, or this amount t, as the base of our triangle. And then we can think of the height as the triangle, because remember the base and the height are perpendicular to one another. So if the base of the triangle is this vertical distance, then the height of the triangle is in fact this horizontal distance. And this horizontal distance is just by how much the equilibrium quantity went down once the tax was put in place, right? So we could say here that this is going to be 1/2 times base times, I'm going to represent the height as our original market Q star minus Q star once the tax was put in place. That this is somewhat of a more precise definition of what deadweight loss actually is. So then the problem continues on. It says, recalling that the area of a triangle is 1/2 times base times height, so we did here. Solve for deadweight loss as a function of t, and then it's going to ask us to graph that as well. So here, you can say, well, we've done most of this. We just need to sub in for Q star and Q sub T star. So we can say that this just gives us 1/2 T. The original Q star was 200. And Q sub T star was just 200 minus 2T over 3. Okay. Make sure you're good with your parentheses so you don't mess anything up. And we get something like this, right? So again, doing some simple arithmetic, we would get 1/2 T times 200 minus 200 plus 2T over 3. So what we see here is that the 200s just cancel out. The 1/2 here cancels with the 2 here. And we're left with deadweight loss that equals T squared, because we have a T here and a T here, divided by 3. So that's actually not so bad. That's pretty simple. And then, again, the question says, graph this relationship for t between 0 and 300. So we can use what we know about math and numbers, right, to say, well, now, again, we're going to have some sort of a parabola, because we have this t squared. But now this parabola is going to be opening upwards, because we can think of this as just 1/3 t squared, so the coefficient on t is in fact positive. So if we were to graph this with t on the x-axis and deadweight loss on the y-axis, we would just be graphing essentially y equals 1/3 x squared, which is going to look something like this here. And again, we can go through, we can draw this to scale. I'm not going to do it this time because it's actually less important. The important part here is that this is going to look like half of a parabola, which we know is curved up in this way here. The last part of the question says, the government now levies a tax on this good of $200 per unit. Is this a good policy? Why or why not? Can you propose a better policy? So let's think about this. So the thing to notice, remember we had 2 equations or 2 results that we derived here, aside from just the formulas for the new market equilibrium once the tax is put in place. We have this formula for government revenue, and we have this formula for deadweight loss. And what we see is that our government revenue, it doesn't keep increasing forever. That at a certain point, increasing our tax rate is actually going to leave us with less revenue. But the deadweight loss is what we call monotonically or always increasing in the rate of the tax. So essentially what we see is for a while there's a trade-off. Then for a while we're saying, well, as we increase the tax rate, we're getting more government revenue out of that tax, and yeah, we're creating more deadweight loss. So we have a good thing, more government revenue, against a bad thing, more deadweight loss. But then once we hit this turnaround point, we're having, a no-win, a lose-lose situation, essentially, right? Because by further increasing the tax rate, what we see is we're actually getting less government revenue. That's bad. And more deadweight loss. That's also bad. And what we can see here, at least in this particular case with our straight line supply and demand curves, what we saw is that the top of this parabola is at a tax of 150. So as the question's asking us about a tax of $200 per unit, that tax of $200 per unit is actually pretty inefficient, because that's going to be somewhere, it's going to be somewhere over here, right? This would be our tax of 200. And you say, well, wait a minute. I could do better. I could both collect more in revenue and also decrease my deadweight loss by, at the very least, reducing the tax from 200 to 150. So in response to the question of, is this a good policy? No, it's actually quite an inefficient policy. And he said, can you propose a better policy? Well, it's unclear what the specific goals of this policy are, whether it's to raise as much revenue as possible, or whether it's to raise this particular amount of revenue. But I could say, at the very least, reducing your tax rate to some degree is both going to get you more revenue and deadweight loss. So at least a general policy improvement would be to set a tax rate or a tax amount of less than $200.